Hey everybody, sorry I'm not able to be there with you today, but I'm doing some good learning, so I thought I'd leave you a quick video with some of the new concepts that we've been working on so that you could do some good learning too. So yesterday in class we worked on an example where you had to decide whether it was a good idea to play a game of chance with an online video game. And as you recall, there were 9 different prizes that you could win, and each prize had was equally likely to be won, but they had different values. And so we're going to talk about this idea of having a distribution or a range of possible numerical values or outcomes for probability experiments. So to do this, I mentioned this term during class. But we're going to define it a little bit better right now. Random variables. So a random variable is actually a set, and we've seen this sort of usage before. It's a set of all possible outcomes for a probability experiment. So for example, I'll give you a couple of examples here. If you're rolling dice, we often use a capital X to represent a random variable. So if you're rolling dice, if that's your random variable, the set of all possible outcomes is 1, 2, 3, 4, 5, and 6. And that's a finite set. They don't have to be finite, but they can be. Each outcome will use an X to represent a specific outcome if we're talking about it in general, and we'll use subscripts like x1 or x2 or xi if we have a general one. Xn would be the largest one, and n is the number of items in the set if there is a limit. As I say, sometimes it can be infinite. For example, you might have all integers are possible. If a set is infinite, it can't have equally likely, all the values can't be equally likely because there are infinitely many of them. That wouldn't really be possible. So let's talk about the 2 different types of random variables. There are discrete random variables and there are continuous random variables. So the discrete ones are like separate values. So if you had a number line, you could put them in order. They don't have to be evenly distributed. They could be clumpy or something. But whatever it is, if you take a value like that one, there is a value next to it, and there's a value maybe on the other side of it. But in any case, no matter what 2 values you pick, or whatever value you pick, you can pick the one next to it, and there won't be any values in between. This area will be empty right here. With continuous variables, it doesn't work like that. They happen on an interval. So let's say this is your interval here. Anywhere within this box, if you pick a value like this one, then there isn't a just next to it value. If you pick any other value that you think is next to it, then in between those 2, you're going to find another value. So a discrete example then, that dice example, if you pick 2, then the next value to that is 3, and there's nothing in between. And it's always possible for the number, if you pick a value like 2, to pick that next value on either side of it. But here, let's say this interval is from 0 to 5, if I were to pick this value 2, then there is no next value to it. If you pick something that you think is close, like say 2.1, then in between you're going to see there's a value 2.05, and if well that's a little closer, let me try to get closer. No, there's 2.01 or 2.00001. There's always another value in between. So that's what a continuous random variable is, as opposed to a discrete one. So we're just going to look at these discrete ones for now, and then later in the course we're going to talk about the continuous kind. So a couple more examples to help understand the differences between continuous and random, continuous and discrete. So here's discrete versus continuous in sort of similar situations. So let's say you have a pedometer, which measures your steps that you take in a day. Then you're going to get a whole number value, something, 0, or maybe you'll get like 5,000 steps, or you walk a lot and you get 10,000 steps. But if even with a value that large, there's always a next value or a previous value. There's this possible outcome, or there's this possible outcome, but you can't get the one in between here. You can't get 10,000.5 steps. Your pedometer is not going to give that kind of outcome. Now, on the continuous side of this is the distance that you walk. So, for example, maybe you walk a lot and you walk 7,000 meters. Well, you could walk slightly farther and walk 7,000.01 meters. Oops, sorry, I started to write centimeters after going an extra centimeter. Or perhaps you walk something in between that, something like this. And no matter how fine you get for this measurement, there's always something just a little bit finer. You could always sort of cut the difference in half and find a value in between. Now, this is limited always by our measuring instruments, but the fact is that it is a continuous distribution of possible outcomes, and we end up looking at ranges or something instead. So as I say, we're not going to be using continuous stuff right now. We're just going to be looking at the discrete kind of variable. So we usually measure something. We usually use x for our random variables, and we use a little x for specific outcome values. And then if we want to talk about probabilities, we have to talk about the probability of a specific outcome or group of outcomes. You don't talk about the probability of a random variable because it's the whole set of all possible outcomes. So what we do is we write something like this: the probability that x equals x. So the probability that the random variable takes on this specific outcome value. And we also will write just p of little x like this. So, for example, if we're talking about the dice, that might be the probability that x is 3, the probability you roll a 3, or often we'll just write the probability of 3. And again, don't confuse this with the permutation notation that we used before. Not the same thing, okay? And we'll do our best not to mix those things anymore. All right. Just got some notes here to make sure I talk about everything. So, we're going to talk about a specific distribution called the uniform distribution. And this is the easiest one that there is for discrete variables. There is a continuous version as well that we'll talk about again later. So in a uniform distribution, there's one important feature. All outcomes are equally likely. That's the big deal. Each outcome is equally likely. That means there has to be a finite number of them. You can't have infinitely many outcomes. So you can see why it's important that it's discrete as well. But you can't have like all whole numbers or something like that. You have to have a limit on the number, and they have to be, oops, sorry about my writing, they have to be known. You have to be able to sort of write them all out. It might take you a while, but it's possible to write them all down. And so that example that we used before, dice, not just any number of dice, but one die, I suppose would be a better way to say this. You've got that limited number of outcomes, and each outcome is equally likely. I'm going to give you a non-example, and that would be the sum of 2 dice, because that list of outcomes is 1, 2, 3, 4, and so on up to, sorry, not 1, can't roll a 1 with 2 dice, 2, 3, 4, and so on up to 12. These outcomes are all possible, but they're not all equally likely. In fact, getting a 2, there's only one way to do that, to roll a pair of 1s. And so that means there's a 1 in 36 probability that that happens. Similarly with the 12, there's a 1 in 36 probability that that happens. But to get a 4, you could roll a 1 and a 3, or a 2 and a 2, right? So then you've got an increased likelihood of getting that 4. And so these Outcomes are not all equally likely, so this is not uniform. It's something else that we're going to learn probably on Thursday. Okay, so that's the uniform distribution. Anytime all the outcomes are equally likely, that's the way it is. So the probability of any particular value, any value x, if I were to substitute in 1, 2, 4, 6, or whatever in this dice example, the probability of any value is 1 over the number of values. Right? So with the dice, or with a die, the probability of a particular value like 3 is 1 over 6. There's 6 values, they're all equally likely, 1 over 6. And you'll notice, of course, that as usual, they add up to 1. You get n of these, n times 1 over n is just 1. All right, we're 11 minutes in. We're almost done. We learned this already. Expectation, or expected value, which we write as E of x, capital X. That means it's the predicted average, or what we expect to have as an average of all outcomes. And remember, it's important that these outcomes have a value attached to them. So the way we calculate this is it's called what we call a weighted average. You take the probability of the first value times the value itself. So the first value times its probability. So that's x1 times probability of x1 plus the second value times its probability plus, and so on, right to the end. X sub n times the probability of xn. So, and I'll just write this with summation notation, and I'll mention this for just a minute. X sub I times probability of x sub I. So this is add up all the values from 1 to n of x sub I, so it's kind of run through all the values of I, x sub I times the probability of x sub I. So x1 times px1 plus x2 times probability of x2, and so on. So it's just what I've written here, but this is writing it out in short form. We're going to practice this because I know we haven't used this yet in this course. So with all of these things being equally likely in a uniform distribution, then we have the expected value is the sum of each of these x's, and then we'll factor out, well, these probabilities are all the same, right? So we can factor out the probability of any x value, so let's say pxn times x1 plus x2 plus, and so on up to xn. So this is sort of like a regular average. Add up all the values, and then, in this case, multiply by a probability, which is going to be 1 over n for a uniform distribution. So that's sort of the special case of the uniform distribution for expected value. So in class we looked at the example of rolling a single die, and remember the possible values are 1 through 6, and then we looked at the expected value or expectation for that roll. And so to find this, if the random variable we call x, that is the value of each possible roll times the probability of each roll. So the first value is 1, and the probability of that roll is 1/6. And the second value is 2, and the probability of that roll is 1/6, and so on, up to 6 times 1/6. Now, because this is a uniform distribution, we can factor out that 1/6 instead, if that makes our calculations easier, because then we'll see that this is 1 plus 2 plus 3 plus 4 plus 5 plus 6 times 1/6, or if you like, it's add it all up and divide by 6, which is what we did in class and what you might be more used to for finding a simple average or a mean. This adds up to 21. 21 divided by 6 is 3.5 or 3.5. So that's the expected value of a roll. And remember, you don't expect to roll a 3.5 on a die. This is simply an average and it's actually a weighted average of the sort of predicted values that you would get. So the more likely a value is, the more its weight, the more its value will count towards this sum that we have. And so that's why in our example with the coins, the prize coins in class, there was a one box that you could get which had a 1 in 9 chance of being selected, and its value was 1,000 coins. And if I had asked you if it was 1,000,000 coins with the same probability, 1/9, would you be more likely to be willing to play? And most of you agreed that yeah, it seemed like that was a good idea. And this is why, because your expectation is going to be higher. If everything else is the same, but you increase one of these values, it's going to increase your expectation, the expected value of a particular, a single outcome. Okay? So, I'm going to be gone for a couple of days. If you need to get a hold of me, you can do that through Twitter. There's my username, and remember, I don't follow you, so you can't direct message me, but we can have a public open conversation if you want to right there. You can get a hold of me by email. Right there. And lastly, you can get a hold of me by commenting on the blog, on this post if you like. mrgraisley.wordpress.com. So hope to hear from you soon, and thanks.